Hi everyone, we're Team 9, Mohammed, Belle, and I'm Shivangi, and we are going to be presenting our work on latent denoising diffusion probabilistic models as a part of our coursework for Homework 5. So, what is the problem we are tackling? We all know that diffusion models are a class of generative models that creates data such as images in this case by reversing a gradual noising process. So DDPM is very good at generating high quality images and has state of the art output. But it requires over 1,000 of these reverse steps, which is very slow inference time, and it also operates in high dimensional pixel space for which massive compute power is required. So we are trying to create a more practical, faster pipeline that can unlock real time applications in, say, vision and graphics. We are building our work on previous work by Ho et al. And Song et al. On DDPM and DDIM respectively. We are integrating latent space compression and classifier free guidance into one end to end framework with DDPM and DDIM. In a nutshell, the task at hand is to implement a diffusion model that generates high quality images of any specific class from a given dataset. Our base implementation was a denoising diffusion probabilistic model, which was completed for our midterm report. After that, we have improved by adding a DDIM scheduler. This was then extended with a latent diffusion model or the variational autoencoder implementation. Then we incorporated classifier free guidance to better guide what the images being generated are. And finally, there will be some additional research that we will be doing to improve the model beyond what we have previously mentioned. To evaluate our diffusion model, we will be reporting the FID, the inception score, and we are considering reporting additional metrics beyond this, such as the negative log likelihood. Our final approach that we present implemented DDPM based on the formulation in Ho et al. Then a DDIM scheduler was added based on Song et al. We then extended it to LDM with a pre-trained model that was provided to us by the 11685 core staff, and finally we incorporated CFG. The datasets we used were initially a CIFAR 10 dataset, which has 10 classes of 32 by 32 images, just to do a preliminary testing of our model. And once we were confident in that, we moved on to the much larger ImageNet 100 dataset, which had about 130,000 images of 128 by 128 in 100 classes. The transforms we applied were resizing the images to ensure consistency. We flipped 50% of the images horizontally. And finally, we applied normalization. Coming to our results, this is what we finally got. These are just two of the images we're reporting out of multiple ablations that we had run. Both of them were trained on A100 GPUs. The entire set of hyperparams has been attached on the side, but to point out the main ones, we have uh, the latent DDPM set to true in both of these implementations, and so has CFG been set to true with a guidance scale of 2.0. In the first image, we have DDIM set as false, and in the second, we have DDIM set as true. Both of these were on ImageNet 100 with 100 classes as shown. This is how our model has improved over epochs. So initially we had very, very noisy results, but then as the training progressed to more epochs, there was improvement, and finally we were able to report much more clear and understandable images. The results in our loss were like we consistently had a plateau of about 0.14 a couple of epochs in. And this is a rest in our conclusion, where we feel that we can try to implement scale linear exponential and cosine beta schedulers to minimize the loss and allow for better image generation to happen, because our loss has been plateaued over 100 epochs. We are also looking to modify unit architecture by adding multi-head self-attention, boost capacity, exponential moving average, etc. We want to do some additional research implementation as well. And finally, we will report our inference results on the model using a validation dataset. Thank you.